So I only solved a quarter cycle, and the results in the spreadsheet show that. Results are, they're not, they could be improved upon. I deliberately kept this fairly elementary. What we're seeing here is the thin blue trace is the copper temperature. I deliberately opened up the air gap to make the copper the dominant loss in this ferrite inductor, which it probably is in a practical ferrite inductor at 10 kilohertz. And so the main thing causing the temperature of the device to rise is the copper loss itself. And you can see the 5 stages of the program. Here's stage 1, stage 2, stage 3, stage 4, stage 5, and the temperature is converging to a steady state. In the temperature model, I had convection and radiation on the external surfaces of the ferrite. So when the internally generated losses equal the cooling, then the device will approach a constant temperature. So this illustrates effectively how we can solve a difficult question. We've got a transient magnetic problem occurring in microseconds, along with a time constant in the temperature domain of probably 10,000 seconds. It seems to take about 10,000 seconds to have this problem converge to steady state. So on the surface, you'd say that's not possible. You have to couple times in the time problems in the same time domain. But by using the ActiveField, we can split that. And my rationale was that a cycle in the first time stage, one cycle is the same as all cycles. So if there's 1 million cycles there or 10 million cycles, they're all the same, so I only need to model one cycle, and furthermore, as explained, I only need to model a quarter of that cycle, so that's how I simplified this problem. So I'm modeling a quarter of a cycle, which is 25 microseconds in a 10 kilohertz sine wave, a 25 microsecond, and then coupling the results to the transient magnetic, which might be in hundreds of seconds, on the basis that all those quarter cycles are the same, so I only need to do one. And then I do the quarter cycle as it gets hotter. But you can see the magnetic, this is the red trace is starting to get nonlinear. It's the magnetic field intensity for a given voltage. So we're fixing the voltage on the winding of the core, and we take what we get with the current that flows. And you can see that as the core gets hotter, we are getting some increases there and some nonlinearity as we're going further and further out on the pH curve. So those results, if you took this further, you would do what I did over here, and I actually combined all the quarter cycles, reversed them, and I made this graph here generate the actual current that was flowing in the winding, because I wanted to see if the device was stable as it got hot. And I deliberately made the air gap large in this case, and that is the effect of diluting or diminishing the nonlinear effect of the ferrite as it gets hot, because the air gap dominates the impedance of this device. But you can see as it gets hot, and the end temperature of this thing was about 120 Celsius, the current is actually slightly rising. It's right on 100 amps there, and it's about 104 amps there, or 102.3 amps there. If you closed up the air gap and ran this again, which I did, then you would see more dramatic changes in current as the device approached its thermal limits. And you certainly wouldn't want to approach Curie temperature with this, because you would get a thermal runaway situation.